Alright, hey everyone. So this is the pre-lab and walkthrough for Lab 3 dealing with atoms, elements, isotopes, electron configuration, and periodic table trends. So most of this should have been covered in lecture. Um, for my course, I post a lot of supplemental videos. For those of you in other lecture courses, you should be past electron configuration, so I think everything is here. If you would like more supplemental videos, um, I can provide them so just let me know which part of the lab you're having problems with, and I can send you a link either from my lecture videos or YouTube that correlates to what you're getting stuck on, which part of the lab you're working on. All right. So, as I said, most of this has been covered, so I'm just going to quickly go over a few points about the lab and then kind of jump right into the PowerPoint. And then I'll finish with these flame tests, which you'll use to fill out your lab report. All right. So, first off, I have posted a PowerPoint. Uh, there is just a small problem, so there's no videos in this one. You don't have to worry about me coming through and playing the video. I will play the flame test toward the end of this walkthrough, um, just to kind of talk about what's going on in the video, but everything should be here in case you need to look it up yourself. Alright, so I would suggest downloading the PowerPoint and then open it through Microsoft Office, through Microsoft PowerPoint, because some of the images get messed up on Cougar View. I'll show you real quick. Let me see, what's a good example? Like here, the writing's a little off the page. In other ones, the image kind of covers up some of the words, or you might not be able to see the entire image like here. So just kind of pay attention to that. I would suggest, once again, downloading it and open it up through Microsoft Office. Then you shouldn't have any problems being able to read all the text and see all the images. All right. Second thing I want to look at is Chem 21. So when you get ready to start your lab, you'll go to Lab 3, obviously, Experiment 3, but you need to open this PDF lab guide, and I'm going to include that in your Cougar View. So let me do that as well. Upload a file. Alright, so this is the PDF lab guide. Um, this has a couple of things that you might need to complete the lab. So number one, it goes through the introduction, the pre-lab, discusses all of the topics generally, and then explains what the experimental procedures are. So it'll tell you exactly what you should be doing. For example, Part A, observe various elements in the lab display. You don't have that, so you might need to look online. Just Google what the properties of these certain elements are. Color, luster. Remember, luster is associated with whether or not it's a metal. If it's metal, it's shinier. If it's a non-metal, it'll typically be dull. Um, Being able to identify them as metals, metalloids, or non-metals. Okay, so this is the procedure part. It also has a lab report sheet that mimics what is on Chem 21. So you can fill this out, but when you're done with this, you absolutely need to upload your answers onto Chem 21 like this here. So I was going to go through and kind of show you how to work some problems, but there's the obvious problem with that is when I work it, it'll end up giving me the correct answer. So those of you watching this have the first row to your lab report filled out here. The correct answer was 16 for the atomic number of sulfur. Yellow was the color dull, non-metal. Okay, uh, but anyway, make sure that you are filling out all of the report sheet on Chem 21. Okay, you can use the PDF lab guide if you want to kind of this PDF lab guide to kind of go along, fill out everything, check your answers, and then start to put them into Chem 21 and see if you got them correct. It also has this plot here, which some of you may need to draw the graph, plot the graph for atomic radius versus atomic number. So just in case you don't have graph paper or something like that, we do have that here. You can print it or get a program that lets you write on a PDF, and then you can go in there and fill out the atomic radius and atomic number. Okay, and as I said, the procedures will kind of explain to you what you need to do. So for that, part F, plot a graph of atomic radius versus atomic number for the first 25 elements given in table 2. So table 2 was up here somewhere, right here, right? 25 elements. You'll plot all these with their atomic radius on that graph. So the atomic radius is on the left side, correct? We'll go back and look at it. Atomic radius is on the left side. Atomic number is on the bottom. So you'll just start at the bottom with atomic number, say 1 on this first line, hydrogen, 2, helium, and label those across the bottom best you can. You might be able to skip a line if you want to. And then on the left side, it'll go up in number as well. So whatever the lowest, whatever your atomic radius for hydrogen or helium, whichever one's lower, you'll start with that number here on the bottom on the left side, and then whatever your biggest number, your biggest atomic radius was from this plot, from this graph table, excuse me. So biggest atomic radius looks like it's 243. So that'll be the max on the left side of this graph. Okay, so you want say 250 up here at the top on the left side, and you can start with 0 on this left side if you want to. Alright, and then just kind of make increments coming up, I don't know, every 10 picometers. PM is for picometers. Alright, so that you should be able to graph that off of this paper. That covers all the procedural things. Let's go ahead and get into pre-lab discussion. I'm going to loosely go over these topics because, as I said, most of this should have been covered in lecture. And in fact, this was 2 weeks worth of lectures that you're kind of getting, that you're reporting on in lab today. But they are more straightforward. You don't have as much hands-on work. Obviously, well, this is a virtual lab, but even if you were in lab, you wouldn't do that much hands-on work. You just pretty much watch the instructor do the flame test, and you complete all of these other little tables and post-lab questions. Okay, so let's get into it. Let me start with the PowerPoint. So laboratory goals. This is a good slide to kind of use to fill out your purpose statement on Chem 21, right? The one that I always put blah 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 on right here. So these slides, if you kind of follow along, should kind of work through in the same order that the lab does. Okay. So the atom we talked about was the smallest particle of an element, but it's not the smallest particle period, because we can break the atom down into smaller things called subatomic particles, right? Every atom consists of protons, neutrons, and electrons. Okay, protons are positively charged, electrons are negatively charged, and when you have the same amount of protons and neutrons, the atom itself is neutral. Okay, so every extra electron will create a -1 charge. Every extra proton will create a +1 charge. So if I have 2 extra protons, 2 more protons than I do electrons, then my atom will be +2 charged. Okay, so and then the interactions between protons and neutrons absolutely has an impact on atomic radius and some of these other things. In fact, chemical reactions or the properties of of an element. Excuse me. So just think about opposites attract. All right, like repels. So electrons try to pull closer to the positive in the nucleus. Electrons on another atom will push away from electrons on any other atom for the most part. Every now and then they can kind of link up and combine, but we'll talk about that later. So, structure of an atom, we're familiar with this. We talk about the electron going around the outside of the nucleus, so your protons and neutrons are real tightly compact in the center. This is a good image here. Protons and neutrons tightly compact in the center, and then the electrons go around the outer shell and kind of make a cloud. Uh, if you're in my lecture, you know I like to think of it as like a fan blade moving. When the fan's going real fast, you can't ever see, you don't really see through it, right? You see the fan everywhere at once, and sometimes it creates this like optical illusion where the fan's moving real slow. Um, Electron cloud is kind of the same way, except for these move so fast it creates a wall, right? I can't ever get my hand in the wall. It knocks it out every single time. So that's kind of how atoms are. The electrons run around the outside so fast that they create kind of a barrier. And the neutrons and protons are in the center, and they are all the mass of the atom essentially, but they only take up a very tiny bit of the atom space, right? Most of the space is empty and is filled with these electrons moving around faster than you can see. All right. So let's keep going. Where am I at now? Okay, so let's talk about the periodic table and what the number of protons, neutrons, electrons means for an element. All right, let me pull up a periodic table real quick. Periodic table. Okay, make sure y'all can still see it. All right, the atomic number, what we call the atomic number, is essentially just the number of protons. Okay, so just following along, hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, so on and so forth. So essentially, the number of protons is the defining characteristic of an element. All right, every element that has 6 protons is a carbon. Every element that has 7 protons is a nitrogen. All right. So, thinking about, let me go back to these slides. Every carbon atom, yeah, every carbon atom has 6 protons. Every copper atom has 29 protons. The protons are the atomic number, and as such, dictate which element it is. Okay? All elements of the same all atoms of the same element have the same number of protons. All right, and all neutral atoms, so a neutral atom, remember we said that if it has more protons than electrons, it's positive. If it has more electrons than protons, it's negative. So every neutral atom has to have the same number of protons and electrons. Okay, so that's kind of a key. That's how you can figure out how many electrons it has. What's the charge on the atom? All right, whatever the element is, that's going to be that atomic number every time, right? If I give you manganese, you're going to go to the periodic table, you're going to look for manganese, you're going to say atomic number 25. That means I have 25 protons. Now, if I go to if I say what is manganese, let's say 2 plus, let me pull up my program. If somebody gives you, that's not dark enough. Manganese, that's magnesium. Do manganese 2 plus. All right, the process is go to your periodic table, right? Look at the atomic number of manganese, which is 25. I'll go back to my paint program and I'll put 25 protons, right? Because that's the atom. Whatever the element is, that's how many protons it has. So I'm starting from there. Now I need to figure out how many electrons it has. It has 2 plus, so that means it has 2 more protons than electrons. If it was 2 minus, I'd have 2 more electrons. Alright, so 2 plus, meaning 2 more protons, would make 23 electrons. Okay, I'm just going to use this little symbol for electrons. Right? So that is how you determine the number of protons and electrons. Let me do one more just to kind of give you an example of electrons. Cut there, and right. Alright, so now say I have manganese 2 minus. Alright, same thing. Since it's manganese, I know that it's 25 protons, but it's 2 minus, so that means I have 2 more electrons. Right? So then that would make 27 electrons. So that's how you use the atom to determine the number of protons, or use the protons to determine which element it is, vice versa. And then the other thing we are concerned with is the number of neutrons, right? Excuse me. The number of neutrons in the atom. All right. So the number of protons and neutrons together makes the mass up. Electrons weigh so little that we really don't count that toward the mass. Remember, mass is a weight. So they weigh so little that we don't count the electron weight in the mass. Essentially, all we do is add up the number of protons and neutrons. Remember, I said all of the weight is held in the nucleus with the protons and neutrons. So, with that being said, if I know the mass of an atom and I know which element it is, like, oh, I'm sorry, let me go back. Let me back up just a hair. Make sure y'all saw everything, that we covered everything. Yeah, okay, so the mass is the weight of the atom. The number of protons plus neutrons is the mass, right? So if I know the element, then I automatically know the atomic number from my periodic table, which means I know the number of protons. It's usually neutral, so that means I know the number of electrons. If I want to determine the mass, I need to know the number of neutrons. Or if I have the mass, I can subtract the number of protons to get the number of neutrons. Let's do a couple of examples real quick. Let me pull up the periodic table. Let's look at calcium. Okay, so calcium has an atomic mass of 40, right? This 40.078 is the atomic mass. And we'll talk about why it's not 40 even here in just a minute when we get to isotopes. But let's just say for now I want to calculate the number of neutrons in calcium, right? So the atomic number is 20. That means my number of protons is going to be 20. Pull this up. Clear all this. And let's do calcium. So calcium, protons equals 20, right? I'm getting hung up on something on my mouse just a second. Alright, protons equals 20. Alright, my mass is 40. We'll just round it off to 40. So, if I want to know the number of neutrons, I can just subtract those two, right? Because all of my weight comes from neutrons and protons, and each one weighs 1 AMU. So, neutrons 20, right? 20 plus 20 is 40, my atomic mass. So that's easy enough. I think everybody should be able to get through that. A lot of good YouTube videos out there, though. If you get hung up at any point, you can obviously go on there and start looking through those and see if any one of them explains it better than I do. I get caught up sometimes trying to do all these little computer programs that I'll skip stuff or uh, miss. I won't explain it as well as I could have. So, anyway, number of protons, this is just a kind of review. Number of protons is the atomic number, which means you know exactly which element it is on the periodic table. The protons plus the neutrons equals the mass number. And you can determine the number of neutrons if you have the atomic number and the mass number. Okay? So the mass number, and this little note here, mass numbers are given for specific isotopes only. That's just concerned with the lab. Alright, that's not like a general statement. Now, let's talk about what an isotope is. If you see a symbol like this, Mg with a 24/12, you need to realize that the top one is the mass number and the bottom is the atomic number, right? And just to kind of check and make sure that you're keeping them straight, you can always go look at your periodic table and check that the 12 is the atomic number of magnesium, right? I'm going to go to magnesium, make sure you're still with magnesium, atomic number 12. Okay, that makes sense. So we know that that is, the atomic number. Now, remember, if I know the mass number, I can subtract. This Mg has 12 neutrons. All right. So isotopes are atoms that have varying numbers of neutrons. For example, I can have magnesium. Let me see if they use that. Yeah, here on the bottom right. I can have magnesium with 12 neutrons, which is the one we just did, 24/12. I can have magnesium with 13 neutrons, 25/12. Or I can have magnesium with 14 neutrons at 26/12. So isotopes are the same element, but they have varying mass numbers and varying number of neutrons. Okay, so as long as they're still neutral, they have the same number of protons and electrons, right? 12 protons is always magnesium, so if you see Mg, you automatically should think that's the same element, the same number of protons. Okay, and this is just kind of discussing what those numbers are. We're fine with that. Elements are pure substances. They cannot be broken down into simpler substances. Pretty much. So anything on the periodic table, if it's on the periodic table, we said you can't break it down anymore. They're subatomic particles, but if I remove one of them protons, it becomes a whole other element entirely. So that really doesn't happen outside of nuclear reactions. Okay. Chemical symbols are the letters that we use to represent the elements. All this is pretty straightforward. The periodic table is an organization of these elements based on properties and the way that they're built, specifically the electron and electron structure. Okay, electrons have everything to do with how things react and don't react. So that, in essence, was the most important part of how the periodic table was constructed. Okay? And you'll see that there's a reason that there are 2 rows on the left side and 2 columns on the left side, 6 columns on the right, 10 in the middle, and then 14 down here on the bottom. Alright? And that is because of the electronic structure, which we'll get to here in just a minute. So we call the columns, we call groups, and knowing the group number is important for electron configuration, but also being able to tell the difference in properties or whatnot. All of my group 1 elements are alkali metals, all of my group 2 elements are alkali earth metals, and then we have other words for the right side like pnictogens and halogens, noble gases. So there are different ways that we can classify these elements, but groups up and down, columns, and then the periods are by rows. Okay, so across the board. Those are called the periods or the rows. Alright, group number, so that's just the number at the top. Typically we skip the transition metals because they follow a different kind of set of rules. So when you count the groups, you're going 1, 2, skipping the transitions, and this going back over here to boron for number 3, 4, 5. All right. It does come back and do 3B, 4B, 5B, and we might talk about that later. It's really just the difference in electron structure, as I said, but we hadn't really got there just yet. The names of the groups. So like I said, scientists like to classify everything, and we got all different kind of ways you can classify the periodic table or the elements in them. Metals, nonmetals, and metalloids are another way of classifying them. All of my metals on the left side of the periodic table, all of my nonmetals on the right, and then you got this little diagonal of metalloids right here on the right side of the periodic table. Okay, so these are just properties of metals, nonmetals, metalloids. You'll probably use some of that for your lab report, so I imagine that's why that's in there. I'm going to look at periodic table trends, but in order to understand that, we need to understand what valence electrons are and electron configuration. Okay, so valence electrons are just the outermost electrons. Right, we said that electrons rotate around the outside of the nucleus and they create this little cloud. So the outermost shell, we like to call them electron shells, the outermost shell is the most crucial for reacting. Okay, those are the electrons that can interact with the environment or other atoms, whatever. So those are the ones that we call valence electrons. Those are the outermost electrons on the atom. And they're actually very easy to figure out how many valence electrons an atom has. If you go to your periodic table, on a neutral atom, the valence electron is just the group number. So hydrogen, lithium, sodium, potassium, rubidium all have one valence electron because they're all group 1. Beryllium, magnesium, calcium all have 2 valence electrons. Remember, skip over here to boron for number 3. Boron has 3 valence. Carbon has 4, nitrogen has 5, right? If I go to any row here, I can follow the same pattern, right? Let's go to row 6, and I'm going to come all the way across to polonium. Okay, how many valence electrons is it? What group is it in? This is group 6. Okay, I guess I don't have my group numbers labeled here, but if I had another periodic table, it'd say group 6. Let's find one. Periodic table? Nope. Images with group numbers. It's too small. With group numbers, yes. Okay, so I'm gonna pick any row, random, come across to here. Let's say iodine. Iodine's in group 7. It'll have 7 valence electrons. Bromine's in group 7. It'll have 7 valence electrons. All right, so that gets you to valence electrons. Let's talk about why they're important. It mentions an exception here. So you see how this top row only has hydrogen and helium? They can only have 2 valence electrons. Okay, that first orbital, which I'll mention here in a minute, can only hold 2 electrons. So that's why hydrogen and helium are up at the top by themselves. They're the only ones that can't get to 8 valence electrons. And 8 valence electrons is like the perfect number. Either you want 0 or you want 8. We call that the octet rule. It's not particularly important for this lab, but it will be going forward for molecules and reactions. Okay, so just quickly mention that, but you don't really have to soak it up just yet. Okay, so we talked about forces, right? Electronic forces. A plus and a minus will pull closer together. Let me make sure y'all can still see this. Um, a positive and a positive will push apart. So that has some indication of what the size of the atom is. All right. So first, let me go to this paint real quick. I want to show y'all something. All right. So let's imagine I have two atoms. Let me see. Let me do one here and one here. Okay. I'm gonna fill this in. So this is the nucleus. Now I'm going to do another orbit that is the first electron shell. I'm going to do one on both, right? And now I'm going to put electrons on here. So let me do that. I can use this, I guess. One. That doesn't look good. Let me just put electrons on here. So I have one on this one, and I have two on this one. Okay? So, we said the opposites attract, right? Now remember, these electrons have little negative charges on them. And then the center, the nucleus, has some positive charges on it, in it. Alright? So, what happens is, when we're talking about atomic radius, the more electrons that I have around this shell, the tighter this shell is going to pull into the nucleus. Okay? So what ends up happening is, if they have the same number of shells, right? Both of these only has one shell, so this would be like a hydrogen, that would be like a helium. The one with the more electrons will be smaller because it's pulling toward the center of the atom more than this one with less electrons. Okay, more electrons creates more of that pull, those positive and negative attractions, and it'll pull that ring in tighter toward the center. So as I get more electrons on the same shell, um, my radius gets smaller. The radius is the size across from the middle of the atom to the outer edge. All right, let me go back to this little chart, and let's see if we can't. I can't really see it. But for the well, you can see it here if you look a little lower on it. You see how these on the left are bigger than those on the right in the same row. That's because they're getting more and more electrons, and that outer shell is pulling tighter and tighter and tighter toward the nucleus. All right. Now, if I'm going up and down, this one's kind of more straightforward and easier to understand. As I go down in row, what I do is I'm adding more shells. Doesn't have to be perfect. I'll just, right? So you see, as I add more shells, I get bigger in size. So that's how come you see this trend here, where as I go down the column, the atoms get bigger and bigger and bigger because I'm adding more and more electron shells. Each row is essentially like adding 2 or 3 shells around the atom. So that's that. Go back to my slides. All right, so now they're introducing the shells. We call them principal energy levels, and they are numbered, and they're also lettered. Okay, so the number refers to the energy level. N equals 1, first energy level. N equals 2, second energy level. And then the letter refers to an orbital. All right. I'm not going to spend much time on the orbital because I don't know how much you'll actually use it going forward. Cancel. I'm not editing. Okay. Orbitals are designated as S, P, D, and F. All right. And just to kind of explain that in terms of the periodic table, let me go over here. So 1 and 2, all of these here are the S block. Helium's actually included because that's the first S block. Alright, so you'll see a pattern here is that the S block only holds 2 electrons. So that's how come it's these two columns or the two groups are included in the S block. Alright, the P block, let me go back to your slide. So that's the S. The P block holds 6 electrons and has 3 orbitals. That's these 3 images here on the right in red. These orbitals are essentially just the pattern in which the electron rotates around the atom. Okay, we said that they all rotate, rotate, rotate. The S just goes round and round and round. The P electrons kind of do this little oscillating thing where it goes swings back around the center like this, but they do them in different orientations. So one kind of goes like this, one kind of goes like up and down, and then the other will go side to side. And they always kind of maintain that orientation. And so when you think about orbital, you can almost think about the way the sun, or excuse me, the way the Earth orbits the sun, right? It's got this set pattern, and that's its orbit. Okay, so an orbital is that, but it's for electrons. Okay, and those are the way that it rotates around the atom. Okay, so S, P, D, F. Each orbital can hold a maximum number of electrons, and that's why I was saying each section of the periodic table is designed. Let me go back to my first periodic table. I liked it. The periodic table is designed to represent these different sections, right? So all of these in groups 1 and 2 are in the S block. All of these from boron to neon are in the P block. Notice that there's 6 electrons. So the P orbital can only hold 6 electrons. The S orbital can only hold 2 electrons. The D is the transition metals from here to here. That's 10 electrons. And then here are the F, and that's 14. Alright, so now let me explain why these numbers here are different. Because each principal energy level, each shell, consists of all of these orbitals, right? So for my first energy level, number 1, I only have an S orbital, so I can only hold 2 electrons. That's how come for the S in number 1 you'll see 2 electrons. Now when I get into the second one, I have 2 electrons in the S orbital, and I have 6 in the P orbital. So for the whole principal energy level 2 is 8 electrons, right? Principal level 2, 8 electrons. Now when I get to 3, that's when I actually include the D's. Alright, so all of these D electrons are part of principal level 3, and they would have 10 electrons plus the 2 from the S plus the 6 from the P, so that makes a total of 6, 2, 10, 18. Right? 18 maximum electrons. And then for the last, it's 14. You won't deal with these much, but 14, I guess that's the fourth energy level. We'll have 14 from the F, 10 from the D, so it's 24, 6 from the P, that's 30, 2 from the S, that's 32. Okay? So that's how they get this maximum number of electrons. But I don't want you to get too bogged down in that. The main reason that you need to know that is to know how to fill in these electron configurations. You need to make sure that when I have a number 2 there, before I move on to 3, I have all 8 electrons filled in. Okay? I can't go to the third principal energy level without filling the second. Now that's not true when you get further down in the periodic table, but I included a video just so that I don't have to fumble through this too much. I included a video on your Cougar View that actually addresses electron configuration. She breaks it down pretty simply, and then shows you how to write, does some examples for you, and kind of works through some problems. So I like this electron configuration video. If you're having trouble with any of this, go through there. Just get used to writing the electron configurations. It'll soak in the more you do it, right? Uh, but this is one of the harder concepts, especially orbitals. I don't think I covered orbitals until I was in organic chemistry. So this is a uh, little bit stronger of a chemistry concept, I'll say. And I'm not too concerned about the ground state. Ground state just means lowest energy level, lowest energy arrangement. So I'm not sure if you're even going to fill out anything like that for this lab. So here's why I was talking about how they divide them into different blocks. The S block, helium is included in the S block because it's still in that S orbital, right? We said that the first row can only have S electrons and it can only hold 2. So both of those first, hydrogen and helium, are in the S block, even though helium's on the right side of the table. Write the electron configuration of the element iron. So I will actually do that for y'all right here, and just to kind of work through an example. As I said, the video on YouTube though does really well. So let me cut all this. Alright, so anytime you're writing electron configuration, you're going to just start counting essentially. First thing I want to do is figure out how many electrons I'm going to have. So let me look back at this and just make sure it doesn't say iron 2 plus or anything. Okay, write the electron configuration of the element iron. Doesn't say anything about charge, so it's a neutral iron. The neutral is important because remember, if it's positive or negative, it has a different number of electrons than protons. Okay, so let me go to my periodic table, see what iron is. Iron is 26, so I have 26. If I have 26 protons, that means I have to have 26 electrons, right? Because protons and electrons, if they're the same number, then the atom's neutral. And it is. So 26 protons, that means I'm going to have 26 electrons. Let me move back to this and start writing. So, as I say, I've done this a lot. I just kind of know where to go, but I will mention something when I get there. So I'm just going to keep filling out electron blocks until I get to 26, right? I had to get 26 electrons. Alright, so next is 2p6 and then a 3s2, 3p6, 4s2. Alright, and now this is when the pattern kind of changes a little bit. So after, remember we said that the D rests in the third energy level. Let me come back to this real quick and just show you what I mean by that. Where's the energy levels? Okay, third energy level, third shell, has 18 electrons. So that means the D's are included on the third energy level. So when I start labeling this energy level, after I get to 4s, I have to go back and address the 3D. Alright, so I'm going to pull up my periodic table and show you what I mean. And if you follow the periodic table, you'll kind of start to put together the pattern, right? 1, 2, so that's all that I do for my S, and I'm restarting on 2. Let me go back to here. Right, I did 2 on the S, and then I restarted with 2. When I get down to here, I did 2s2, 2p6, that got me to here, 3s2, 3p6. Notice that I didn't do anything for D because there's no D's there. When I came from magnesium to aluminum, it was a straight jump. So 3s2, straight into 3p6, and I fill out all of those. Now I'm getting to the row where iron is. My first one that I'll do is 4s2, but now I'm putting in D's. The D is actually on the third energy level, so when I write that in, I have to put 3D, and then however many electrons is just how far it is on the periodic table, or you can count the number of electrons. I'll do both ways. Periodic table, 1, 2, 3, 4, 5, 6 electrons in the D orbital. Excuse me, sorry about that. 6 electrons in the D orbital. So let me write that down. 6. And now just to check, I'm going to count the total number of electrons here and make sure that it matches that 26 there. So 2, 4, 4 plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 6 is 26, right? Let me show you all that one more time so you know where I'm counting. 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20, and then 20 plus 6 is 26. Okay, so they follow the same pattern every time. If you do a couple that are further down on the periodic table, like say, make sure I didn't lose y'all just then. Like say barium or molybdenum, I'd stay above this F region. Okay, once you get to here, 57, you actually jump down here and start adding in your F. So I'd stay above that, like niobium, molybdenum, chromium, maybe work some on this right side like iodine. You know, that's 53 electrons, so it's going to be a long electron configuration. But if you get it right, I mean, you've pretty much covered all the bases for doing electron configurations. All right. So I recommend doing some practice with that and just kind of double checking. Once you do it, you can type in, hey, what's the electron configuration for gallium? And Google will show you, hopefully, the electron configuration that you should have written down. So just a way to kind of check yourself and make sure that you're doing everything right. And so that's the example of electron configuration, how they're written in, and what those little orbital things are, right? So those are just these little blocks that we designate electrons with. S block, P block, D block, F block, F orbitals. Alright, go back to PowerPoint and see if there's anything else that we need to cover. For the flame test, so electrons, when they absorb energy or emit energy, those electrons are actually moving from energy levels. So the color that comes off can indicate what kind of atom it was, because we know that electrons, the distance, or excuse me, the energy that the electron moves with will dictate the color. Okay, so seeing that color can tell you whether or not it's a certain element, right? And so what we do is we put flame to it. That flame is essentially throwing a bunch of energy into the atom, and then whatever energy comes back out will tell us kind of the structure of that atom, where those electrons were on that atom, right? So that's how the flame test works. Let me see if she does anything with it here. Mainly groups 1 and 2 have the characteristic colors. This is kind of a diagram of what happens. So the energy from the fire or whatever is pumped into the atom, and then the electrons are excited They jump out to a higher energy level because they have more energy. Remember, the further it gets away from the nucleus, the more energy it has. So as it gets further away from the nucleus, it has more energy, and then eventually it's going to go back to the ground state that we mentioned earlier, the lowest energy, um, the lowest stable energy form. Once it goes back to that ground state, it's going to throw off that extra energy as photons, and that's how come you see the colors. All right, so that's just what this diagram is representing. And they do it. Let's watch the video of these flame tests, and I think that'll be about it. So there should be some kind of diagram that explains the color. It might be on your PDF here. Let's see if it's there. Flame test. I don't see anything about. Let's see. You might have to Google it. I might Google this. Flame test colors chemistry. All right, this is cool. So remember, it said that most of the good colors come from groups 1 and 2, and you'll notice that a lot of these are in groups 1 and 2. Not all of them. There's iron and copper, some other ones, boron, that are outside of those groups. But I like this little diagram. But all of them should be roughly the same. Um, for these, just make sure that you're focusing on groups 1 and 2, right? Or a metal. Um, Typically, colors are not produced by nonmetals. So if you see like chloride, 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 sulfur, sulfur, uh, typically those don't produce color. So whatever else is there is what's producing the color. So lithium produces the color, strontium produces the color, calcium produces the color, sodium produces the color. You get the drift? All right. And all of those are in groups 1 and 2, by the way, also. So boron is in group 3, copper's a metal, potassium's group 1, potassium's group 1, magnesium group 2. So a few metals do it, but most of them are groups 1 and 2. This will kind of give you some hints as to what the element that's being excited in creating this color is. So you can kind of use these images. I didn't include one on Cougar View. I guess I could. Which one would be the best? See, that one seems confusing because I don't think she'll give you that many different ones. Download option. So just yeah, I guess y'all can find this on your own. You see that I typed flame test colors chemistry, and then looked at the images and started kind of pulling those off. So last thing we'll do is watch this video for the flame test. I've included this in Cougar View as well, um, and it should be Jamie performing these flame tests for you, and then she'll test an unknown, and you need to determine.
We're going to do a flame test on a number of selected compounds.
Oh, that's not Jamie.
Group 1 and 2 ions. And these are aqueous solutions, and we have just a inert metal loop. We're going to dip the end into the solution and put it into the flame. And that excitation, characteristic color, is like a fingerprint for an element. So we're going to look at a number, and then we're going to ask you to identify some unknowns. Potassium. It should be a lavender. This is barium. It's a green. This is calcium. Calcium. Sort of a yellow-red. Strontium. This one's a pretty red one. Lithium. Sodium is a bright yellow. And then the last one is copper. This is the most vivid of all of them. That's green.
All right, so that's it there. Let me just make sure. What does the unknown say? Copper, calcium, barium, potassium, strontium, sodium. So I think all of those are covered there. Um, for unknown, I guess you didn't cover it. Let's just put 1 for unknown A. It really doesn't even matter what you put. If you want to put 1, 2, or 3, just it might say it's wrong. Just make it, take it, and I'll fix that when I go back and grade. And then the electron configurations, the number of outer shell electrons, group number, row number. I think you should be good there. All right, so I think that's it for today. Let me make sure I covered everything I wanted to cover. Go back to the slides. Looks good. All right, so y'all let me know if you have any questions. Um, I'm getting started on the grading. If it gives you, some flack about feedback or not letting you turn in answers, you can email me before you get to your last try if you want me to kind of look at it. More than likely, though, it's a problem with the tolerance or whatever that thing is. So, uh, still haven't figured out how to set those correctly. I'm working on it. It shouldn't be as big of an issue for this one. More so with the math and large numbers of significant digits, right? Which none of these really have. So straightforward. Um, there's a lot of help on YouTube, obviously, if you need it. And then I can provide some more videos or work some examples if necessary. So just email me. I'll be around all weekend. This lab is not due for another like 10 days or so. So you have plenty of time to get on this and get working on it. Uh, and you'll have time to get in touch with me and get some feedback if you need it. So that's it. I will see y'all next time. Bye.